One of the most important laws in all of physics is that of the conservation of energy. And it even comes up in this course here in sort of limited form, but there's some very interesting things we can do with it and as we start to learn about this very important law. This video won't possibly do something as large as conservation of energy the justice it deserves, but we have to get started somewhere, and there's a lot of other reading and things you can see about how energy is conserved. But it is an extremely important law in physics, so we'll just try to cover it a bit here with a bit of a sort of a cartoon example. So the way I'll start this is just to ask a simple question here. There's a light bulb that's run by electricity, and you can imagine a light bulb in the room you're sitting on being on. So the question is, how is it that the light bulb is on? And so the very first thing you might answer about that is because it's plugged into the wall. And that's a good answer. So you can imagine the black cord coming out of it like this, and you look on the side of your wall here somewhere, and there's a wall outlet right there. Maybe you have two of them or one, whatever, and the light bulb's plugged into that. So that's a good answer. That's why the light bulb's plugged in, because that's why the light bulb's on, because it's plugged in and someone turned it on. Okay? But being a scientist, being curious, and studying about conservation of energy, let's take it a bit further now. So you might say, okay, well, why is the wall outlet allow the light to come on? What's the wall outlet connected to? And then you might think, well, the wall outlet is typically mounted on a wall. That's why it's called a wall outlet. And somewhere inside this wall where this thing is connected, there's some wires running through there. They might go up to the attic or down or whatever, but there's some wire in here for sure, like that. And so then the question might be now is like, okay, well, what are these wires connected to? And you might think a bit more and you go, oh, well, I know what my house looks like sort of from the outside. I'll just sort of draw it over here. So we're going on another figure here, sort of like your house right here or whatever you're in. And you're inside here. Maybe the light bulb that we're talking about is like in here or something. And it's glowing like that. And we see the extension cord of the light bulb going over to the wall where the wall outlet is right there. And we know that your house sort of might be near things that look like this. Sort of these big poles. And you know, these poles, and maybe one's like way down here. And you have these wires attached to them like that. And one of the wires, those comes over like to the roof of your house. There's a little holder right there. The wires comes right on down to the roof of your house like that. And you might think, well, the wires over here in the wall that the wall outlet are connected to, probably at some point connected to a big box on the side of your house which has a meter on it, which maybe someone comes by and reads from time to time so they can charge you. But then that box goes up to this thing here, which goes up to these big lines here, which just go off like forever. They go off somewhere, who knows where. These are these power lines. They go off some of the very high voltage on the top, and birds land on them and stuff like that. And so that's sort of a pretty good answer that takes it at least a little bit farther here. The light bulb's on because it's plugged into the wall, and the wall outlet is connected behind the wall to some wires. And you look at a more sort of outside your house picture here, you see the light bulb on, and you know that the wires behind the wall are probably connected in some fashion to this box that's on the side of your house that has a meter on it that gets read, how you get charged for electricity. It goes up to this pole here, which is on your roof, which goes up onto these electrical lines, and you don't often see where the electrical lines end. They just sort of go on forever. But we'll continue because we still haven't really answered the question is why the light bulb is on. We're just sort of seeing a bunch of interconnects here. So I guess the next question we should look at then is where do these power lines go? Well, at some point the power lines, through a variety of mechanisms that the specifics aren't all that important, power lines sort of keep traveling along. They keep going along and along, and at some point they sort of have to stop, and they come to a big building here. They go into this big building, and this big building sits here, and it's called the power plant. Power plant is sitting there. So then the big question is, as we're talking about this conservation of energy here, is, well, all right, what's inside of a power plant? So it turns out, at least in the United States, most power plants that are give electricity to cities are either run on coal, natural gas, or nuclear. So in other words, these are the types of power plants that you'll find: coal, natural gas, or nuclear. Now there's some very small efforts for solar, for wind, and those sort of things, but the dominant ones, at least in the United States, are coal, natural gas, and nuclear. And that's what's inside the power plant. So the question is, okay, well, technically then, my light bulb, which is the original question here, is through just a variety of technology and wires and poles and things, is more or less directly connected to the power plant, which is either coal, gas, or nuclear, natural gas, or nuclear. So the question is, all right, what is inside of the power plant? We're just continuing on our journey here because all we really discovered about our light bulb is what it's connected to, but we still haven't really answered the question about how is it that a light bulbs come on. Okay, so what we'll do is look inside the power plant. What typically you'll see inside of a power plant then is a big tank of water, actually. It's a big tank of water that'll look like this. So there's the tank. Here's the water like that. And the tank is usually closed. It doesn't have an open top, but there's a little bit of outlet right here, a little bit of outlet where, well, something can escape. So let's just talk about that. So you have this big tank of water here with a little bit of an escape valve on the top. And what you do under the water there is you light a fire under it. Something like that. Something equivalent here. You get something really hot underneath the water. Probably isn't directly a fire depending on what type of plant it is there, but in either case something gets really hot. Now what happens to water when it gets really hot? Of course it begins to boil. And when water starts to boil like that, steam starts to come out, and that's why we left this little opening right here. So some of the steam can escape out like that. And you know that steam is very high pressure, so it's going to come shooting out. That's what makes your tea kettle whistle and that kind of thing. So here's the water here. And here's the steam that's created because somehow we produce all this hotness underneath the water right here. Now what will happen is a couple of things. There's a lot more things to talk about, but at least in the simple picture right here, the steam here is directed directly at blades of a turbine here, turbine. And you have to take another physics class to understand how a turbine works, but essentially what happens over here in the turbine is you can think of this sort of as another sort of machine in itself. Maybe it's in its own box like that here. There's a couple things in here. There's some very large magnets, and there's a lot of wire in there, and the whole thing spins. And it turns out that when magnets move, wire moves inside of a bunch of magnets, what you'll get on the wires that come out is electricity. And there's a lot more that you can discuss here, like for instance, is electricity going to be AC or is it going to be DC, and all sorts of considerations, and how much voltage does it have, all these sorts of things, and the power, and there's just a bunch of parameters that will come out of that. But in a nutshell, it's this hot water producing the steam, and the rushing steam that comes out causes the turbine to turn, and that's where electricity comes from. And so these connections here that come out of the generator with some processing and some other technical things that are just way beyond the scope of this discussion here, these lines here are essentially the ones that are going to go out and feed those power lines then that eventually go all the way up, and go into your house, and they're connected to that light bulb. So it's something about a turning generator that turns a light bulb on. So we sort of have that going now. And so the question now is like, that you have there is like, all right, well, where does this heat come from? Looks like the heat's very important to boil the water and get the turbine to turn here. So that's the interesting question. That's about where our conversation will stop here, because in order to make this hotness right here, you have to burn something. You have to, because that's where the heat comes from. So in this case here, we burn coal, or we burn gas, usually natural gas, NG natural gas, or we allow nuclear reactions to get really hot. Either way, this burning process here is what produces the heat that gets the whole process started in there. And so that's about where our conversation will end. That's why your light bulb comes on. But you have to think about it a little bit. The answer still isn't so direct, but essentially the light bulb comes on because we burn something. That's why the light bulb comes on. Now, what does this have to do with conservation of energy? Well, on the two endpoints of this chain right here, you can see that over here where there's the coal, natural gas, and the nuclear here at the power plant, inside the power plant even, not just the walls of the power plant, but actually deep inside the power plant, the thing that drives the whole thing, is this burning process, and that's where the energy cycle really starts for that light bulb to come on. Now, after you do this burning, you get the hot steam, which turns the turbine and the wires and the magnets and the AC and the DC on out to your light bulb here. This is really sort of like the end of the process over here. So it starts with the burning of the fossil fuel or the fuel over here and ends with the light bulb coming on. That's the whole chain. How is this tied into conservation of energy? Conservation of energy is tied into this because everywhere along this rather complex chain of events that has to happen to make the light bulb turn on, you can track where the energy goes. So that's really what conservation of energy is about here. It's about tracking energy. And so for this process here, you can track where the energy goes all the time. So let's just start, say, with a lump of coal. So you can start with a lump of coal, which you can think of as something like a black briquette that some people use for barbecues. You just start with this thing, you dig it out of the ground and process it. So there's some energy spent right there in the trucks and the backhoes and things like that. But in either case, let's just start with the coal. So the coal is a form of potential energy. There's a bunch of energies that we've discussed sort of in a different video here. So coal is a form of potential energy because it has the ability of doing something, making some action or doing something making some change, but of course has to be brought out. Now the way we bring about that change is we burn the coal. So as soon as you burn the coal, you start the energy release, and you might have something like, a fire or some flames. If you imagine your barbecue pit getting really hot, you'll see these red hot coals sitting in there, and that's exactly the energy release. So see, there's a little bit of energy conservation right there. We go from the black brick, which we can hold in our hand, which is very messy, and suddenly we can make it glow and get hot. So there's some energy release. But then we have this hot steam. And so when we get to this point right here, we can also track the energy as we go, okay, the steam came from heating the water, which came from the hot flame, which came from the coal. Then you say, well, now there's this turbine turning in here, and you can probably hear it turning. It's going, it's whirring and things like that. And like if you stuck your hand in there, you'd get hurt, and there's some energy of motion in there. So you might think of this turbine in here as some sort of kinetic energy over here. And you might think of the steam over here, maybe some sort of chemical energy, if you want, or something like that, because the water has been separated from its neighbors and formed into this gas here and is sent out to turbine. So again, the kinetic energy of the turbine came from the chemical energy of the steam, came from the heat being released from the coal, came from that black brick of coal itself. But the process goes on, of course, because as you have this electricity coming out of these wires right here, you'll hear the electricity humming, something like that. And it's very dangerous up here because there's very high voltage up here. They can sort of spark when it gets too rainy, or it can potentially kill a bird that lands on it the wrong way, or whatever the case may be. And even these wires here might get a little hot because of all the current traveling through them. And so we see another form of energy in there. Again, starts from the coal, goes to the heat, goes to the steam, turns the turbine, but now we have humming power lines, sort of another form of energy in here, the of the power lines in there. And then when it goes all the way into your house right here, you can see the light energy inside your home here that allows you to see. And if you touch the light bulb will be nice and hot, because some of these incandescent light bulbs are very inefficient. Something like only 10% of the light actually goes, 10% of the energy actually goes to light. So if you put your finger on this thing here, it'll be like it'll be hot. And you might even say, ouch, it might even be too hot to touch, that kind of thing. But again, you see the energy chain where it went. The heat and light of the light bulb came from the electrical energy in the wires, which came from the kinetic energy in the turbine, which came from the chemical energy in the steam, which came from the energy being released from the coal, which originally came from that black coal brick area. And that is what conservation energy is about. It's about tracking energy. At all points through the stage here, we can say where energy went. Say where energy went. And that's what conservation of energy is all about. And we'll just end with one last thing. No one said that this process is perfect here. So we're always saying where the energy went, and we're keeping it kind of global, saying it went from the black brick to the hot fire, to the steam, to the kinetic energy, to the wire, to the light bulb. Now we settle that pretty global, and it's not perfect because all these systems always involve energy loss. We know that. But we can still track where the energy went. So like for instance here, when we burn the coal, sure, some of the heat goes into heating the water up, and that's certainly where we want it to go. But some of the energy also just leaks out, because this fire, say for instance, is contained in, say, a big black metal kettle or something like that, and some of the energy is just going to heat the side of the kettle here and just be wasted. It's going to heat the side of the kettle, which will heat the side of the building, which will just escape and make the air hotter into the environment. It was just lost. But we still are able to track the energy. Yes, we are not able to recover it to make our light bulb come on, but we still are tracking where the energy went. And then some of the steam here can't be contained. As soon as the steam comes out of this nozzle right here, it might immediately sort of catch on some higher part of the metal structure here and just immediately condense back into water or something, or it just might evaporate away into the room or into the atmosphere. It does not go into turning the turbine, so it will not go into producing electricity, but it's still some loss in there. So we'll still draw more of these little loss arrows going out. We could lose some energy in here as well, but we still tracked where it went. And then we know that power lines are very inefficient for transferring energy from one place to another. Depending on what you read here, maybe 50% of what you put into the power lines are just lost in the transmission process here because of the resistance in the wires and so on and so forth. So there's going to be more loss in here, more of these arrows indicating energy going out. So again, it's not a perfect system. We are saying where the energy goes. We're not saying it all goes to the light bulb. There's going to be some loss in there, but nonetheless, off it goes. Then even in the light bulb, of course, we know from some experience here that only about 10% of the electricity that actually gets the light bulb goes into making light. So there's a lot of heat loss right there, but we still are able to track where the energy went. So this has been a long video. It is now over, but the conservation of energy is about the ability to track where energy goes during every phase of a particular process. And in the next video, we'll see how that actually applies to simple physics problems.